All right, so what we were doing last time is we went through and derived a solution in ODE, or sorry, a PDE, and then we wanted to convert that into the S domain, right? And we're trying, we did our transform into the S domain, and we now need to get that solution back into the time domain. Right? So we had this example we're working through, trying to go from time to the S domain using the Laplace transform, and then we want to use inverse Laplace. In order to use inverse Laplace, we have to break out our solution into a bunch of terms, basically, that we can do the inverse on. And so this task that we're going through now, as far as we got, was getting down here to this state here, where we said, okay, if we look at our table, we know we can do this inverse pretty easily. It's just S plus some constant. So that becomes the exponential of that thing. So, so that's as far as we got. I just want to wrap up this example and go through the inversion of the other two terms here. So let's continue on and do that, and then we'll move to 1D Laplace transform. Okay, so this is our first term. We had the exponential. So now let's go and do this term here. Okay. So let's write this out. So that term is going to be t infinity divided by tau times s. What's going on here? Tau times s times s plus 1 over tau. Okay, and we want to break that up, right? We have, in the denominator, we have an s, and we have an s plus something. So we want to break that up so we can do the inverse of those separately. So let's make this equal to some constant C1 over S plus some other constant C2 over S plus 1 over tau. Right? If we go through, that was, I think, one of the first examples we did is different factors in the denominator, you break it up. Okay, so we want to go through and solve for these constants. All right, to do that, we are going to start by multiplying this entire thing by the denominator at the left-hand side, which is tau s plus 1 over tau. Okay, and then that gives us this equation, t infinity is equal to c1 tau times s plus 1 over tau plus c2 tau times s. Okay. And then let's see, we do a little bit of rearranging here. Looks like it's exactly the same thing. So now we just have to group based on our s coefficient, right? So we have s to the 0th power terms, and we have s to the 1st power terms here. So we'll come up with two equations for those. So the 0th power, what is that? That's going to be, on the left-hand side, we have t infinity. And on the right-hand side, we have just, C1 times, what is it doing here? C1 over tau, right? Oh, no, because it's tau over tau. Okay, so it just becomes C1, right? Hopefully I did that right. C1 times tau times 1 over tau, right? So it just becomes C1. Okay, the second one is on the left-hand side, we have 0 s to the 1st is equal to what's on the right-hand side, that's C1 tau plus C2 times tau. Okay, so we have our two equations here, two unknown constants, we just solved for it. So let's just keep moving here. So then that gives us this equation. So our first term becomes, it was t infinity over tau s plus 1 over tau. So that is the equivalent statement there is t infinity over s minus t infinity over s plus 1 over tau. Okay, so that's our equivalent solution there. Okay, hopefully we're right there. So that this becomes the thing that we substitute in for that first term. Right? We're now breaking this up into these two pieces. Okay, we can do the same thing for the second term, this term here. So let's go down and do that. So we've just decided this is our first term, this is our last term. Now we just have to break up this second term. Okay, so we'll kind of go through this a little quickly. It's not terribly interesting, but this is G dot triple prime max over, let's see, rho C S plus 1 over A, S plus 1 over tau is equal to, we want to break this up into the repeating terms. So we have S plus 1 over A and S plus 1 over tau, and then we have some other constants that are multiplying that. So what we want this to become is something like C3 over S plus 1 over A plus C4 over S plus 1 over tau. Okay. So we do the same thing we've done before. We're going to take this entire equation and we're going to multiply through by this denominator. Okay. So we multiply through by that, and then we're left with, what are we left with here? So we're left with G dot triple prime max on the left is equal to C3 rho C S plus 1 over tau plus C4 rho C times S plus 1 over A. Yes. 1 over A. Okay. So then we have, let's see, we have S to the 0 and S to the 1 in this equation. So S to the 0 is going to be, let's just write this out. So if we do S to the 0, we get G dot triple prime max is equal to C3 rho C over tau plus C4 rho C over tau. Or sorry, rho C over A. Okay, C4 rho C over A, and then S to the 1 is going to be, in the left hand is 0 equals C3 rho C plus C4 times rho C. Okay, so again, we have two equations here and two unknown constants, C3 and C4. And we can solve for those directly. So we have now broken up our entire solution into things that we could theoretically invert using our Laplace inverse. Okay. So let's see how to write this out. Let's see. This is one more step here. So where are we? Yeah. So let's write out the full solution together, and you'll kind of see how this comes. So our full t hat, right? T hat's a function of s. The full solution is going to be the first thing we did. So that's t infinity over s minus t infinity over s plus 1 over tau. Okay, and then the second term becomes our C3. I'm just going to write C3. We have solved for it explicitly, so we could solve for that. Sub in the actual constants, but I'll just keep it as C3 for now. So C3 over S plus 1 over A plus C4 over S plus 1 over tau. And then the last term was plus T infinity over S plus 1 over tau. Right? Every single one of these, now we can go back to our table and we could invert them one by one and take them back to the time domain. Right? This is now really easy to do. Actually, if you look at this, let's see, what do we have here? Oh yeah, so this term here, minus T infinity over S plus 1 over tau, and plus T infinity, those actually go away. So we're just left with three inverses that we have to do. Okay, if you do that, that becomes T in our time domain now. Inverse is taking us back to time, is equal to T infinity plus C3 exponential of minus T over A plus C4 exponential of minus T over tau. Right, where C3, this one, and this one are the coefficients we get from solving here, right? These are not unknown coefficients. This is our actual full solution now in time. Right, so we just remember that process. We took the inverse to get to the S domain. We enforced, in that process, we enforced the initial condition, solved for T of S in the S domain, and then did the inverse back to time. And then we have our actual full solution with the initial condition enforced in the time domain, okay? So that's the solution there. Let's actually real quick take a look. This is just my placeholder slide to remind me to go to Maple and EES. So we could look at the EES solution, but actually it is really easy to do these lump capacitance problems directly in Maple. So Maple, despite the fact that we went through all this by hand, it's really easy to do this in Maple directly. When you get to certain problems that actually you can't do it in Maple, and so it's good to understand the process. Let's take a look first at Maple. So let's see. Okay, so we're going to come into Maple and let's solve it here. So we'll restart. We're going to load our library. Right? We need our Laplace and inverse Laplace functions. And then here's the ODE, right? This should be the ODE in time that we started with. Should be exactly the same thing. Let's just double check that. Oh, okay. Let's let this, I'll talk through this while we're loading. Okay, so we're solving this in time. All right, so this is our ODE in time. Should be the same thing. And so what I'm going to do is I'm just going to take the Laplace transform of this function that I just wrote in time with respect to time into the S domain. Okay, so there's our Laplace. And some things to notice, right? You can tell it worked because, well, it's still saying I'm taking the Laplace of this function of time. You can see it's multiplying S in here. It's got some other things going on. If it just comes back and kind of repeats the command at you without doing anything, you know that it didn't work, okay? So we'll see that it worked because it's actually multiplying through by S's and doing something. It did introduce this thing, t at time 0. Okay, so our next task is going to be, let's make that substitution. Let's figure out how to put in what the thing is at time 0. As you're going through this, so you might kind of find that it's a little cumbersome to be carrying around this Laplace time to S, right? It's a little bit of a messy to say that. So what we've been doing is we were calling this T of S or T hat of S. So let's actually just sub in. Anytime we see Laplace of this mess, let's just call that T of S, or we could call it T hat of S. Let's just do that. Okay, so here's now the solution with our T hat appearing. Now let's sub in for that T of, oops, just happened, T of 0 condition. And we know that at time 0, the solution has to be T infinity. Okay, so we're just subbing in our known initial condition into the previous function. And then we want to solve this for T of S. Okay, this is our solution in T of S. We could, you could go through and convince yourself that this is equivalent to the thing we just did by hand, but it is. Okay, and then now we're just going to ask Maple to do the inverse here. So we're going to take this whole solution in T of S, do the inverse back to the time domain, and you see, in fact, it works. Okay, so this should be the same solution. Okay, so Maple's really good at these 0D problems, but when you get to 1D problems, it kind of sucks, unfortunately. Just to make it fun, that's what we're doing for homework. Okay, so let's look at actually taking this in EES. So let's say we took our solution. This is what I just solved for right here, and I copied it directly from Maple and put it here. And then let's compare that to the analytical solution. Right? This thing actually has an analytical solution. I think we went through at one point and did that. I hope we did. Anyways, here it is. So let's compare what we get from Maple to the analytical solution we get before. So all of this up here is just the analytical solution. So we solve that, we get a result. Okay, so it worked. And then I've gone through and plotted it for a bunch of different times. So we compare the temperatures at different times. And this is what we get, right? So this is what we get. So you can see the solution we did manually, this blue line, analytically, is going to match what we get from Maple. So good. So it worked. All right. So this is just another tool that you have now to tackle some of these problems. The Laplace transform it can be really powerful because it simplifies the solution process down in the S domain. The challenge is always getting back to the time domain. Okay.